pretty sure I have nightmares about forgetting to record a lecture. Or even almost worse is when I am on mute for some reason, because that's happened actually. And so that's pretty bad too. But so far, well, now that I've said it, wouldn't that be annoying? No, it looks like I'm okay. Okay. All right. So, sounds like you guys have had a look at the assignment 1, right? So that's really good. Can't remember if I warned you guys or not. You have 10 attempts, but after it's supposed to be on the 3rd attempt, then if you still get it wrong, then it starts taking 10% off per attempt, right? So you've got 2 free ones is what it's supposed to be, but if you're finding that that's not the case, then let me know. Is that what you're finding? Yeah.
Yeah, because I was like 0.3. Yeah, I was wrong.
See, it's not supposed to do that. But that's what I was hearing from Joya, who teaches the other section. She's like, yeah, for some reason, it just knocked you down right away. And so we don't want that to happen. So so I will make a note to myself to have a look at that, right? And so let me go here. Yeah. So, assignments, oops, can't write it all today. Assignments, I'm going to say you should have 10 attempts per question, right?
Yeah.
Good. It's so hard because like no matter what they do, they've got the student view and all that kind of stuff. But for some reason, my view is always a little bit different. Like when I try it, it worked, obviously. I wouldn't give it to you if it didn't. But then when I give it to you guys get something that's slightly different. It's very annoying. But anyways, so we'll get it handled. So you should have 10 attempts per question. But minus 10% per wrong attempt after the first 2, right? So if you get it wrong on the 3rd attempt, that's when it should be taking marks off. So I'll have to go in and check to make sure, right? I can see your attempts and stuff, so obviously I can see if it was right away, and I can just change it. So that's going to take a little bit of manhandling on my end, but not to worry. So after the first 2 attempts, so you get 2 freebies is how it's supposed to be. So just so you know what to expect. And then if it's not doing that, then send me an email. But I will have a look around. Okay, so just so you guys know, some things happen in the department. We don't know what's going on, but a coworker of mine is not able to teach, so I'm taking over his class, which is right after ours, which is actually cutting into my office hours. So I'm gonna have to bump my office hours by an hour, I guess. So office hours will be from 11 to 1 Mondays and Wednesdays instead, right? And I don't know how long that's going to be going on, but we'll just keep the hours or the office hours that way for the rest of the term. And then, because we don't know if it's going to be for the rest of the term or what's going on. So office hours are now from 11 to 1. I think they were 10 to 12 or something like that. Hey, that's cutting into my lunchtime. And I love these new stations that they've got up. Term 2 is always awesome. Anyways, that's, maybe if you stop by and it's close to noon, maybe that's where I'll be. Hunt me down in the caf. Mondays and Wednesdays. But you can always stop by. If I'm in my office, you're more than welcome to ask me a question. If I really don't have time, I'll just tell you, sorry, I don't have time. But usually I do. Right? So, yeah, so you can always stop by. You can always text me. You can always email me. You can always get in touch with me. So, or anytime. Right. All right. I feel like that was all the housekeeping. You got a formula sheet. All right, this one's yours to keep. What's going to happen is for the test, you'll get fresh ones. I'll print off fresh ones. So these ones you can write, make notes on, just have for when you're doing your homework and stuff. I don't give it to you on the first day of classes because I'm worried that you'll run away scared. But don't be scared. We're going to master this thing. So we're going to work through it block by block and just kind of tackle them as we move through the course, right? And so, and it's just really rewarding when we get to the end and we finish our last block, because that's how you know we've covered everything, right? And so today we're going to get into the first block, let's call it descriptive statistics, right? And so that's why I had to give it to you, okay? So you know what's on there. It looks a little bit beastly, mostly because there's a lot of different formulas that we could use to calculate the same thing, right? And so there's tweaks on the formulas, right, depending on how you want to approach it. So we'll talk about all those. But let's do a quick little review, right? So it was just on Monday, so just a quick review, right? We talked about, okay, well, how can we visualize numerical data? Usually we had a bunch of different options, right? But usually we visualize numerical data using a histogram, right? And so we visualize numerical data using a histogram. Talked about some others like the dot plot, the stacked dot plot, the stem and leaf plot, right? Those are all kind of by hand things that you should probably just make a histogram, right? And then I mentioned that the only one that I might make you do by hand is a box plot. So we'll talk about those today. But so we visualize the numerical data using a histogram, right? And from that histogram, we're able to look and decide what the shape of this distribution is, right? And use this to determine the shape of the distribution. And so we talked about the shape being, well, what's going to be our go-to is this beautiful normal distribution. Which we said, okay, well, it only has one peak, and remember the peak is the mode, right? And so this is a unimodal symmetric distribution, right? If we had to describe it, right, there's one peak and it's symmetric around that peak. And so it's unimodal and symmetric. And then we talked about some other options, right? We talked about, well, we can have things that are kind of looking like this, right, with a long tail. This would be skewed, right? Skewed is always in the direction of the tail, right? And so this would be skewed to the right. Skewed to the right. It's still unimodal, right? It still only has one peak, right? One distinct peak, but now it's not symmetric anymore, right? Because it's skewed in the direction of the tail. And we talked about, at least for me, when I started seeing these things, I always wanted to talk about the lump, right? Where most of the data points are, right? And who cares about those extreme points? But in stats, we have to kind of shift our thinking, because in stats, what we're going to be interested in is those extreme values, right? What's going on? What's happening over there, right? We're going to be concerned about those extreme values, right? And so it's always skewed. And I shouldn't blur it so much when we're first writing it. It's SK EWED, skewed. But whenever I write it, it ends up looking like shoot. Skewed in the direction of the tail. In the direction of the tail. Or, of course, the opposite, right? This would be skewed to the left. Secretly, I have to do the left and right. Check my left and rights. Oh, left. You can also say positive skew and negative skew, right? So this would be positive skew or negative skew, but usually I just say left or right, but whichever one you want to use is fine. And then we got a little crazy and we said, well, we can actually have kind of distinct humps like this, even if they're not, you know, symmetric like this. They can be kind of wonky off to the sides, right? But this would be bimodal. Or if you have more than two distinct humps, right, or two distinct modes, I guess I should say, right, then you've got a multimodal distribution, and we're not going to talk about those in this course, right? So for us, we're going to focus on the normal distribution, right? And what we started saying was, okay, if we have a normal distribution, then what we have, right, is we have this whole other box of tools that we can use, right? Because if we have a normal distribution, we're able to use the mean or the average as our measure of center. And just being able to use the average as the center is really powerful later on in our calculations. So if we have a normal distribution, we can use, I said, I'll say we can / should, right? We're only allowed to use the average as the center if we have a normal distribution, so that's why I say we can. But it's also the most powerful thing that we have going for us, so that's why we should. So we can and should use the mean, which we introduced last day, right? And that's just, we usually just call it the average, but now I want you to think, okay, mean, average, I can use those interchangeably, right? And so we use the mean, which is just the average, as our measure of center. And then I said, well, if I gave you a set of numbers and I asked you, hey, what's the average of these numbers? You would add those up and divide them by however many you have, right? we all know how to find the average of something, right? But what we probably don't know is the notation for finding the average of something. And so we said, well, x with a bar over it, it means the mean of x, right? So anything with a bar over it is going to be an average. Right? Anything with a bar over it, a bar over it, tried to combine those two words, bar over it is an average. More specifically, a sample average. So you can have X bar, you can have Y bar, or my favorite, your average smiley face. Here all day. So, I guess I shouldn't say average. I should say mean. But it just doesn't, it's not as funny if I say the mean smiley face. But maybe it is funny. Anyways. Do I need to make a note here? Probably not. Anyways. Okay. So, that was kind of new, right? So this is kind of where we transition from the review into kind of new stuff. And so anything with a bar over it is an average, right? And so we'll call that the end of our review. And so even though saying that it has a bar over it was kind of new. So we've got the sample average. We did sort of mention, right, that, okay, well, the whole game is going to be, well, we're going to take sample information to try to learn something about the whole population, right? And so we're going to have a sample mean and a population mean, right? And we're going to use that sample mean to try to know something about the population mean. And so we need notation for the population as well, right? And so our population mean is going to be denoted by mu. And I think I did it all big for you guys, but I'll do it again. So it's kind of like this fancy M, right? And this is a Greek letter mu. This is, you say mu, yeah. And this is the population mean. In general, right, population things, right, means, and then when we get into standard deviations, the variance, all those things. So all these population measurements we call parameters, right? So any measurement from the population is called a parameter. And I'm going to say all parameters, but there's later, way later in the course, I'm going to use just the normal letter. I guess I could use pi, but it gets confusing. I use p instead of pi, but you could use pi, which is a Greek letter, right? So I'm going to say any measurement from the population is called a parameter. And for now, all parameters are denoted by Greek letters. So we'll get pretty good at the Greek alphabet as well. We also said that any measurement from the sample, any measurement from a sample is called a statistic. It's called a statistic. So these are the ones that are going to be denoted by just our regular alphabet, or just with a little hat or a little bar or little tweaks on it, right? But in general, these are all going to be from the sample, and so they are called statistics, which is what we're studying. So X bar, right? If we go to our formula sheet, right? Your formula sheet says that X bar, there's two different formulas. One is the condensed formula, right, with sigma notation. And so that one looks like 1 over n times the sum of the xi's. I'll remind you guys here, this is a capital sigma, and you're going to read it as the sum of, and then whatever follows it, right? So the sum of all the x's. The subscript I is just denoting each observation, right? So if we're looking at this front row, 1, 2, 3, 4, 5, 6 observations here, right? 6 people in the front row. And so I'd have xi in general, right? But x1, x2, x3, x4, x5, x6, right? These are my observations, right? And so we just use the subscript I to denote, oh, any and all observations, right? All observations that I'm looking at. And I usually write this formula like this, right? I just put the sigma, so the sum of all the xi's over n, but that's the same, right? If I have 1 over n times the sum of the x's, then, well, I can combine those. The sum of the xi's, we can expand to be x1 plus x2 plus x3 plus ... plus xn, remembering that n is my sample size, right? So my last observation is going to be the last one in my sample, right? N is the sample size. And then all that is divided by n. All right. So you don't really need a formula for that, right? It's on your formula sheet and it looks a little nasty, right? But as long as you remember that, oh, I actually know how to calculate the average of 10 numbers or something like that, right? Then you're okay. All right. So we said the mean is going to be our measure of center, right? If we have a normal distribution. So now, and we also talked about, and I forgot to write it in the review, but we also talked about, okay, well, in order to fully describe a distribution, right, we need to talk about the shape. In this case, we're zoning in on a normal distribution, right? We can talk about or we need to talk about the center, but we also need to talk about the spread, right? And so to fully describe a numerical distribution, we need to discuss the shape, which for now, I'm just going to split into normal versus non-normal. And I know that's kind of a cop-out, but we can just chisel it down to just those two categories, right? Either it's normal or it's non-normal. Right? The center, which we've only talked about a normal distribution, right? Which is the mean for a normal distribution. It's not very helpful. Sometimes I write normal with a capital N. Sometimes I write it with a lowercase n. It doesn't really matter, right? But I want you to remember that the normal is a name, right? So it's not saying, oh, this is normal. Well, it is too, but that's where the name came from, right? But it is the name of the shape. Okay. So as a little sneak preview for the center, we're going to talk about using the median for a non-normal distribution, right? And we haven't talked about that, and it'll be a little bit. Median for a non-normal distribution, which I'll just write dist, because I ran out of room. Third thing we need to talk about is the spread. Right? We haven't talked about the spread yet, but we need to know what the spread is. How much variation are you expecting to see? Right? And so for a normal distribution, we use the standard deviation or the variance. You'll see that the variance is essentially the big brother of the standard deviation, right? And so the spread, we use the standard deviation for a normal distribution. And typically we use the interquartile range, just as a heads up, interquartile range for a non-normal distribution. So for now, let's talk about the standard deviation and the variance. So the standard deviation is a measure of the variability in your data. A measure of the variability in your data. Okay. For example, right, if we think about, let's talk about dogs, right? So dogs, there's lots of different breeds, lots of different types of dogs, and they come in all sizes, right? But if we're talking about the length of a dog, right? Just because I want to talk about the length of something else later. So the length of a dog, considering all breeds. So our population is just dogs, right? We're expecting a lot of variation in there, right? We know there's small dogs, we know there's big dogs, we know there's medium dogs, right? And so we're expecting this kind of large range. If we then talk about mosquitoes, mosquitoes are typically very uniform, right? And if we see one that's even a little bit bigger than most, we would say, whoa, that was a big mosquito, right? And so we've got this extreme observation, right? Because we know that the variation in mosquitoes is not, we're not expecting it to be very big, right? And so depending on what we're talking about, right? If we see a difference of even 2 millimeters in a mosquito, we would go, whoa, right? And not just because they're really small, right? And so 2 millimeters is a little bit bigger. But even if we saw that big of a change in the length of a dog, we would say, oh yeah, sure, that can happen, right? Because we're expecting this larger spread, right? And so we're not really as confused by that much variability in the dogs as we are in mosquitoes, right? And so knowing how much variation we're expecting, right, that's going to be important to be able to determine if something's extreme or not, right? Which we said, well, that's what we're heading towards talking about, right? And so we need to know the variability, or the spread, I'll put in brackets, right? The spread, in order to be able to determine if an observation is extreme or not. Right? In order to be able to determine if an observation is extreme. And so, oh, so question, hand? Oh, so I'm just talking about the variability, the spread in general, right? And so the standard deviation is going to be a numerical measure of the spread. And so the standard deviation is a numerical measure, start over, is a numerical measure of spread. Oops, can't write it all today. That's all right. So a small standard deviation means that you're not expecting very much spread at all, right? So a small standard deviation, can I just write SD? Usually in writing, we abbreviate, I'll do it properly, standard deviation, but usually we just abbreviate it SD in writing, and then in the math we use just S. It gets a little confusing, but so a small standard deviation SD means that we expect very little variation in our data. Means that we expect very little variation in our data. Whereas a large variation or a large standard deviation means large variation in our data. Right. And so what we would say, right, is the mosquitoes would end up having a small standard deviation, right? And so I'll put in brackets after the small standard deviation mosquito example, and then the large standard deviation would be the dog example. So we need to know the shape. We need to know where is it centered, right? So on what value are we expecting most of these things to fall on? And then we need to know the spread, right? How tight around the center are all these values going to be, right? And so I usually try to think of it as, so you're on the phone with a friend and you're like, oh yeah, I'm looking at this distribution. Do you want me to tell you all about it? Your friend says, oh yeah, definitely. Yeah. Okay, cool. No. So then you say, okay, well, it looks like it has a normal distribution. Oh, wow, that's awesome. Oh yeah, and it's centered on 10. Oh, okay, cool. So now we know, okay, well, I know it's symmetric, right? So your friend's like, okay, symmetric, unimodal, centered on 10, right? So most observations are going to be around 10, and a standard deviation of, get this, 0.5. What? That's crazy. Those are so small, right? So everything is going to be centered around 10 and very close to 10, right? So even an observation of, let's say, 13, right? If you're expecting a standard deviation of 0.5, right? An observation of 13 would be considered very far from 10, right? And so that's where we're going to be headed, is just, okay, well, taking into account the center, right? The mean, and the standard deviation, right? How much spread we're expecting to see. Well, is this thing going to be considered far away or extreme or not, right? Or is it just going to fall in the middle, right, with everyone else and be boring, right? So, so the standard deviation is usually the one that we use in calculations, and the variance is kind of the, like I said, the big brother of the standard deviation. The variance is the standard deviation squared. Okay? And so the variance is also a measure of spread. So the variance is also a measure of spread. In fact, it's the standard deviation squared. In fact, it is the standard deviation squared. So your standard deviation, if you look at your formula sheet, right, you've got an S squared and an S, right? Just ignore whatever follows those formulas for now. We'll break those down, right? But so the S squared must be the variance, right? If the S is your standard deviation. And so S, a lowercase s, is your sample standard deviation. So because it's from a sample, right, it's a statistic, right? So anything that we've measured from our sample, they're all going to be statistics. Whereas S squared, right, we said the variance is just the standard deviation squared. And so this is the sample variance. Or we can take it the other way, right? Well, then the standard deviation must be the square root of the variance. Or the standard deviation is the square root of the variance. Either way, you slice it or dice it, doesn't matter. Okay. So make a little note to yourself that in writing, right, we abbreviate standard deviation by SD, right? And in our calculations and in our math, we just use S, lowercase s, right, for the sample standard deviation. Just like we had a population equivalent, right? We've got a population equivalent for the standard deviation and the variance. And so a lowercase sigma, which is just going to be a little, an O with a tail on it. Okay. So a lowercase sigma you can just read it sigma, right? But I wanted to specify because we already saw capital sigma, right, in the summation. So this is a lowercase sigma, is the population, bless you, standard deviation. And then same idea, right? Sigma squared is the population variance. Now, if you continue past this course into stats, because you had so much fun and you love it so much, and you feel like you finally tackled the sample and the population stuff, right? Then what we typically use is the variance for the spread. But because using the standard deviation makes things a little bit easier, in this course, we're going to focus on the standard deviation. So all our formulas are just going to use the standard deviation instead of the variance. But just remember that, yeah, no, they're the same, right? Wherever I can use the standard deviation, I can just use the square root of the variance and vice versa, right? So for us, in our calculations and things, right, we're just going to use the standard deviation. So I guess I should have any questions so far. I'm just blah, 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 blah here. All right. Okay, moving on then. So yeah. So that would be a capital sigma. Yeah, yeah, I know. Got to get our Greek letters all in a row. So here, I'll just make a note here that capital sigma, this is a capital sigma. And this is summation notation. Fun to say, fun to do. No, not that fun to do, but fun to say. Summation notation. Right, and they're going to behave completely differently. Okay, so should we look at how to calculate the standard deviation? You've got a little sneak preview here. And so to calculate the standard deviation, we have a few options. And this is just a matter of taste, which one you like more. Yeah. Let's start with just going on your formula sheet. S squared, it says, is 1 over n minus 1 times the sum. So far it's looking kind of similar to the average, right? Except instead of over n, we've got over n minus 1. Right? So far, so good. And then the sum, now instead of all the x's, we actually want to take the sum of xi minus x bar squared. Right? That's a little bit nasty, right? But from here, if that's our s squared, that's our variance, right? If I want to use this formula to find my standard deviation, right, I would just take the square root of this. So s is going to be the square root. And I actually, the formula sheet has them separated, and I think that's just to make it look a little bit nicer. But I actually like them smushed on top of each other, right, instead of having to write the 1 over n minus 1 and then timesing it. So what I'm going to do is I'm going to write that same equation, the sum of the xi's minus x bar squared over n minus 1. And then because it's not s squared anymore, I've taken the square root of both sides. So everything has to go under the square root. Most common mistake that I see is you get to the very end and then you forget to take the square root, right? And so you're so close. So just remember to take the square root when you're doing these calculations. So what's this saying? Well, we've got the familiar x bar, right? So we know how to calculate x bar. X bar is just the average, right? And so what it's saying is, it's saying, okay, well, ignore the summation for a little bit, right? And for each of the data points, subtract the average, right? So see how far each of these data points are from the average, right? So you've got your data probably in a list like this, whether that's in Excel or whatever, right? So you've got your data listed like this. And so each data point, then you make a new column, or I do, right? Each of the data points minus the average, right? And the average stays the same, and you're just seeing how far are all these things from the average. And then we have to square each of these things, right? And so then I make a new column of the previous column squared, right? Each individual item squared. Then we have to add all those up, right? So then we add up everything that's in that column. And then we get a number that we can divide by n minus 1. And n minus 1 is just taking into account that it's a sample. It's not important. It's just something to remember. And then we can take the square root to find the standard deviation. Right? So, or, deal with this page break here, or another way that you could do it, right? And maybe this is a little bit easier. I actually like the previous way, but I was looking at some of the questions that you have to do in the assignment, and it uses the sums. And so, or you can use s squared is the sum of the xi squared. So what that's saying is you want to square each of your data points, right? So you have to make a new column with each of your data points squared, but then you just sum all those up, right? So you don't have to subtract the mean anymore. And then minus n, which is your sample size, times x bar squared, right? So the average squared. Yeah. Over n minus 1. So on your formula sheet, right, you've got both formulas for s squared, so that's why I wanted to show you how each of them behave. But there's only this one for s, even though there are two for s, of course. And so s, we're going to calculate as the sum of the xi's squared minus n x bar squared over n minus 1, and then take the square root of that. So this is the one that we're going to use So let's see here if I can steal some numbers. Whenever I think of numbers, they don't, or like make up my own data. So standard deviation. Oops. Standard deviation calculation example. Find the mean and standard deviation. And standard deviation. Oops. There. Of the following data. So I'm going to steal just the first, let's say the first 5, just so we're not here all day. So 69, sorry, you don't know what I'm looking at. There's 10 to choose from. I'm just going to pick the first 5 just to have an example. So 69, 86, 74, 71, and 86. 1, 2, 3, 4, 5. Sure. Oh, and I guess these are the weights of 10 adult male German Shepherd dogs. A dog theme. Fun. So these are just 5 adult male German Shepherd dogs. Actually doesn't matter what the data is about, right? We just need to know how to calculate this thing. So first thing, let's find the average, right? We can find the mean. So, oh, so fast. I gotta write it all out. So X bar, right, is the sum of all these values over n. And so we've got 69 plus 86 plus 74 plus 71 plus 86. And we have 5 data points. So divided by 5. I didn't write out the formula that we were about to use. The only reason for that is because sometimes I find that the formula for the mean throws you guys off. So you know how to calculate the average, so we can just jump right into it. Typically though, I like to show the formula that I'm about to use and then use it, which you'll see when we do the standard deviation. So, oh, you said you had it, sorry. 77.2, and no more decimals, just plain old 2. Phew, great. All right, that makes it easier. Because if we had a ton of decimals, I would probably say round to 2 decimal places, right? And then when you have to use the mean, if I've asked you to round it previously, you should just use the rounded value, right? So usually I say keep all your decimal places, keep all your decimal places. But if I've asked you to round the answer, you can use the rounded value later on, right? So in this case, I definitely want you to use all the decimal places if I don't specify. So 77.2, that's our mean. So now we can start thinking about calculating the standard deviation. And so our standard deviation, let's write out the formula. S is, and this is the one on your formula sheet, I should write it out the same way that it's written, the sum of the xi's squared minus n times x bar squared over, oh, turn my 2 into a square, which is pretty funny. Let's see here. 69 plus 86 plus 74 plus 71 plus 86 divided by 5. I'm getting 77.2 though too.
It might be in order of operations.
Oh yeah, did you add them, hit equals, and then divide by 5? There you go. Yeah, so I would probably just add them all up, hit equals, and then divide by 5. Cool. Over n times x bar squared over n minus 1, and then square rooted. So here, usually what I would do is I like to make a table because it's just easier to deal with, right? And so what I'm going to do is I'm going to make a table. 1, 2, 3, 4. Oh, and I'm going to try to squeeze it in on the same page here. A little crowded. So I've got my x's, my xi. Those are just my observations, right? And so I'm going to make a column of my observations, which the first one was 69, 86, 74, 71, and 86. I gave myself lots of room. I guess I didn't. With the sums of squares, you don't really need as much room as I gave myself. But anyways, so over here, right, we found that the sum of these things was, oops, times 5, 386, nice. So here, we said that the sum of the xi's is 386, right? If we just add up all these, we get 386. And then that's what we divided by 5 to get the average. So now, if I make another column, if I want to have at the very end here, right? If I want to add up and have the sum of the xi's squared, right? That's different from the sum of the xi's squared, right? Here, we have the xi's squared and then summed, right? And so the order is going to matter there. So for us, what we want to do is we want to make a new column of each of these x's squared, and then find the sum, and that's the value that we replace that first bracket with. So if we make xi squared, 69 squared is 4761. 86 squared is 7396. 74 squared, 5476. 71 squared, 5041, and 86 squared is 7396. If I add all these up, right, and it gets annoying because these are big values, and often they will be big values, or even have decimal places and things like that. But at least if it's boring, then that means that you know what you're doing. So it's just kind of this machine that you run, right? And you're just kind of like, okay, now I got to square them. Yeah, that's going to be boring and take a long time, but oh well. And so I actually kind of like, well, I really like tedious work actually, because it makes me feel like I know what I'm doing, right? So at least I can sit down, calculate a standard deviation, and feel really good. So 4761 plus 7396 plus 5476 plus 5041 plus 7396. Dun, 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 dun. So the sum of my xi's squared is, I get 30,070. Hopefully that's what you guys got. Seeing some nods, so. Okay, so now, right, we said, well, we know our X bar, so now what we can do is we can put all these values into our formula, right? And so here, you know what I'm going to do? I'm just going to rearrange a little bit. You don't have to, it's just for space reasons on my end. There. Where did this go? There. Hey, there's a square on here. There. Just to kind of reorganize a little bit. So this value here is going to be this value here. And from before, we know that X bar is 77.2. And so that's the value that's going to go in here. And then N is just our sample size, which is 5. So what we have is, and have I told you guys that I want you guys to stack your equal signs as often as you can, right? So if you're writing something, then your equal sign, there are times when even I can't get them to stack up for space and whatever reasons, right? But as often as you can, just try to stack your equal signs, definitely not working across the page, although sometimes it's really tempting, right? And there are times where I'll do it too, but in general, for big calculations like this, I want your equal signs stacked, right? So that's nice and clean to look at. Okay. So I'm gonna do the square root here because we're just gonna leave that until the very end. And in place of the sum of the xi squared, that's where I'm gonna put the 30,070. And then I'm gonna minus n, which is 5. And I know my X bar is 77.2, and I want 77.2 squared. Only the X bar is squared, right? If the n was also squared, I would have had to put brackets around there, right? But because there are no brackets, it's only the X bar that's squared. And then divide that by 5 minus 1. Should make my 5 look less like a 6 there. So, okay. We've got our 30,000, which I'm going to leave alone for a little bit. What I'm going to do is I'm going to simplify, right? I'm going to simplify this lump and also simplify this to 4 and just kind of move slow and steady through here. And so I'm going to write my square root again. 30,070 minus, and then 77.2 squared. Thank you. And I'm going to times it by 5 just because I can. Make sure though that you get as your answer here 29,799.2. Divided by 4. Okay. So you want to deal with that lump first, and then you can subtract all of that from the 30,070, and then we divide by 4. Okay. So now 30,070 minus that guy. Usually your calculator will have a previous answer button, and I use that quite a bit. Right? So if I just calculated the 29,799.2, then I can just do the 30,070 minus my previous answer, right? And so a lot of this is going to be getting to know your calculator so you can save yourself some work. So now I have the square root of 270.8 over 4. So divide that by 4 first, and I get the square root of 67.7. And I'm always so sad when people just stop at the 67.7 because you've forgotten about the square root. And that's why it's so important to keep that square root hanging around always so that you can remind yourself that you're not done, right? And so here, finally, it's been s equals, s equals, s equals, but because I've got a little page break here, I'm going to say s equals the square root of that previous answer, and I get 8.228000972, which I'm a stickler for even that's an approximation, right? I know it keeps going, it's just my calculator clunked out. So I like to do the approximately equal. It's not something that I expect you to do, but it's a good reminder to yourself that, hey, if I'm looking at something like this on my calculator, I understand that it keeps going, right? This isn't an exact answer. So for the approximations, I use the squiggly equals. And so 8.23, let's say, to 2 decimal places. As a default, we can use 2 decimal places. Question.
Do we have to write out equal numbers that's on our calculator, or can we do it right away?
You can go to it right away. I'm gonna write out the full answer. No. So you're safe. As long as you're rounding properly. Right? So, all right. Oh my goodness, time flies when you're having fun. All right. We've still got some time though. So what else did I want to say about the standard deviation? Probably nothing. Well, probably many things, but none of which are important. So let's just talk about non-normal data, right? And we said, okay, well, starting over, right? What's our measure of center for non-normal data? I gave you that sneak preview. It's going to be the median. And so for non-normal data, we use the median as our measure of center. The median is our central value. So the central value, and so this is the data point that separates the lower 50% from the upper 50% of your data, right? So the one that chops it in half. So the data point that splits the lower 50% from the upper 50% of your data. In order to do that, right, we have to sort our data from smallest to largest first, right? Our smallest 50% from our larger 50% or the upper 50% of our data, right? So we can't just have unsorted data. So our number one thing is we're going to have to sort our data from smallest to largest. To calculate the median, step one is that we have to sort the data from smallest to largest. And then on your formula sheet, it has the location of the median is n plus 1 over 2. That only tells you the location, so you still have to count in and find the actual value, right? And so I actually find that pretty confusing. So usually what I do, and your data sets will always be manageable, right? Once I've sorted my data, I start from the outsides, and then my patent pending boop, boop, boop method, boop, 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 boop. There it is, right? And so then I use the boop, boop, boop method to count my way in, making sure you don't go cross-eyed because it does get very like, what's going on here? Boom, 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 right? And then if you land on one number, that's the median, right? Usually I circle it. If I land on two numbers, that can happen. I just take the average of those two, right? To find the median, we use the average sometimes, and that's weird, right? But that's just what we do. So to calculate the median, right, there is a formula for finding the location, but I like to use the boop, boop, boop method. Another boop. Has to be 3 boops. Boop, boop, boop method. Patent pending. No. To find the central value. Right. If you land on one value, circle it. That is your median. Right, that's the value of your median. If you land on 2 values, circle both of them, and then draw a line down the center to indicate that that's where the median is, right? And then take the average of those 2 values as your median. So circle both and draw a line down the center to indicate that's your median. And find the average of the 2 values. And find the average of the 2 values. This is your median. So just to show you, I'll give you the data of those 10 German Shepherds, just because it's nice to have a larger data set. 69, 86, 74, 71, 86, and then 100, 68, 99, and then I need 2 more. So I'm going to scoot this over a bit. 99, 65, and 62. And so we're going to find the median. So the first thing I have to do is I have to sort these from smallest to largest. Right? And so as I go, usually I put a little check mark or something to indicate that I've used it. And then once I've sorted them, I always count to make sure I have the same number, right? So you didn't lose one. So I think it goes from 62, 65, 68, 69, 71, right? 74. Nice. 86, 86, boom, boom. And then 99 and 100. So here, now that we've sorted, right, just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. Now, okay, here we go. Boom, 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 boom. I said boom instead of boom. Screwed it all up. Here we landed on 2 values. So I'm going to circle those 2. So just to double check, it's easier when they're right in front of you. Boom, boop, 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 boop. And then I draw a line here, and then I say, well, my median is 71 plus 74 over 2, which is what? 72.5, right? And so that's your median. Ditch the 100 and go with 9 and try that at home. Otherwise, I'll see you guys on Friday or on Monday if you're not coming to the lab. Oh, and read chapter 3 for next week. I know I told you to read it for today, but. Hey, Alex. See you later.